Good morning and welcome everybody to this course of Fundamentals of Machine Learning over Networks. It's a great pleasure to see so many of you here, and many more have registered and will be attending this course also online because all the lectures and videos will be recorded, as you can see, and uploaded. I would like just to say a couple of quick words. This course has been entirely created by Dr. Hossein S, Ghadikolaei, who is here, and is a postdoctoral researcher in my group, and jointly with the University of California, Berkeley, in the group of Professor Michael Jordan. And then the course has been together also created by Professor Ghadikolaei, who is a newly assistant professor at Telecom Paris in France, and he was until very recently a postdoctoral researcher in my group. My name is Carlo Fischione, and I am with the network, and also Dr. Hossein S with the Department of Networks and Systems Engineering here in KDH. And I am acting mostly here as course responsible according to KDH rules. I will only give one lecture to this course, and there will be later on. And now my word goes to
Thanks, Carlo, and thanks for everybody for being here. As Carlo mentioned, this is a course that we tried to put together in the last few months, and the materials that you will see here, some of them, I would say until lecture 4, essentially, they are like standard textbook, actually until lecture 3, I would say, standard textbook materials, but then afterward, you're gonna see that we need to jump on the edge of the developments in these fields, mainly in optimization and machine learning, but I would say actually mainly optimization. Feel free to interrupt at any time, and then it would be much better if we can have some form of interactive class, okay? So the first lecture, introduction. What we're gonna see in this lecture is we're gonna first start with some logistics of the course, saying how the course works, and then the contents of the course, and then finally we'll go through the lectures to somehow overview what you're gonna see future in this course. So first, it's a 10 credits. So let me have a shortcut here. So this is a 10 credit PhD level course if you're a master's student, either over the net or here sitting. If you're a master's student, unfortunately, you cannot get any credits up to now. But then I heard that these credits can be transferred to you if you are going to be a PhD student here in Sweden. We have a total of 13 lectures. The first 8 lectures covers the fundamentals and required backgrounds, and the next 5 lectures are somehow formalized in the form of special topics. You will see what does that mean. But then essentially that the special topics are somehow form the form of a workshop where you would have a combination of oral presentation and poster presentations there. We will see later on what are included in those special topics. We do have student groups for homeworks and computer assignments and those oral and poster presentations. And the way that it works is for individual person, it could be a bit hard and time consuming to do the homeworks and computer assignment, especially computer assignments. So we were thinking, since we have so many participants, then I guess that we can go for some groups of 4 to 5 students per group. You are free to form the students groups by the end of the next lecture. So you have this lecture, the full week, and the next lecture to form the groups. And just let us know by email what are the names in the group. Group members, the thing is that if due to any reasons you are not here physically, or you can't find the group members, just contact us, and then we will help you to form the groups. This is very important, forming the groups, because everything will be shared within the group, and the way that we're gonna give the credit, it's based on 0-1 loss for group. So everybody in the group either pass or fail, okay? And then in the homework, you're gonna work together in the group, and we randomly, so the way is like, at the beginning of the next lecture, we randomly select one of the groups for every homework or computer assignments, and they're gonna come here, and then they can use either their laptop or the board to give everybody the solution. And if you're happy with the solution, so if they're okay, then everybody in the group gets the point of that homework. Otherwise, nobody in that group will get that. And it's not required for everybody of the group to present. It's just one just enough, or two is enough, okay? So make sure that one or two from every group is in the class. And if you cannot come, you should let us know beforehand, okay? In general, we have actually 3 homeworks now and 6 computer assignments. Again, this is just for groups. And as I mentioned, delivery is in the next lecture, and random group selection, okay. And then there are some optional assignments and some final research project. And then, but these guys are optional. As I mentioned, we will move very fast toward the edge of the technology in this field. And that's why that there are lots of open problems here that you can think of. It's not really hard to find those open problems. So it would be very interesting to have some form of collaborations within some of those groups here in the class. Any question? Okay, good. Just some suggestion. Since the homeworks and computer assignments are designed in a way that you need to have some good theoretical background, some good understanding in the research, and some good programming. So try to somehow use all those skills in the group formations, okay? Then let me move here. For up to now, we have over 100 participants, and 39 of them are outside Sweden, and then they're gonna watch the video. So the way is like, we're gonna record the videos and then put everything on YouTube afterward. If you have any question, just email us. You can find us through these emails, and please use MLON in the subject if you want to be sure that you will get your answer. You can see all the materials in the course website, and we're gonna upload everything in this YouTube channel. At this point, we don't have any Google group or any other form of group where you can discuss, but then if you think that is necessary, then we can just open up some groups where you can have some form of active discussions over there. Just let us know if it's required. So, what is included in the course? I would say that this course is at the intersection of these things, essentially. So we're going to have a lot of machine learning here, but it's just nothing but optimization, a combination of optimization and statistics here. You will see a lot of them. And then we would have networking. Well, what is the meaning of networking? It's going to be clear more in the following slides. But in optimization, we're going to cover convex optimization, non-convex optimization. And when we combine optimization and networking and, of course, machine learning, then the problem gonna be how to model these things. So the modeling could be the modeling of the communication overhead, the modeling of the iterations complexity, the modeling of the network, objective functions, constraint functions, and how we can do the programming there. If we're gonna go for distributed implementation or parallel processing, then in that case, we're gonna tackle this communication efficiency problem. So this course is somehow intersection of all these keywords. Okay, so if we jump to the first big keyword of the course, it's machine learning. So generally speaking, we can somehow divide the machine learning topics or concepts to unsupervised learning, supervised learning, and reinforcement learning. So generally speaking, in unsupervised learning, we're going to learn from some form of unlabeled data. So you're given a set of unlabeled data, and then the main question is find some common features, common behaviors in the data set. So essentially clustering, and a very prominent example is like k-means clustering. In supervised learning, on the other side of the spectrum, examples are like deep neural network or support vector machines or whatever like that. You're given a set of labeled data, and from that, you're going to find the mapping between input and output. The better you can find the mapping, the happier you are. In that class, depending on the class of the labels, the class of the labels can be discrete set, can be real or anything. So depending on the class, you can have some form of problems in the form of regression or classification. Okay. And then finally, reinforcement learning. Prominent example is like SARSA or Q-learning algorithmic approaches, where it's fundamentally different from unsupervised and supervised learning in the sense that you're going to learn by interacting with some unknown environment. So you're given an unknown environment. You don't have a data set a priori. You might have some data set. You might have some noisy things a priori, some prior belief on the environment. But the whole idea is that you really don't know entirely the environment, and you're going to interact, and you allow some, intentionally actually, you allow some suboptimal actions, which is not the case in supervised learning. So in supervised learning, generally you're given a data set, and the ultimate goal is to find the optimal action, and you are not allowed to do suboptimal actions because nothing is there to explore. But then here, due to this exploration, you're intentionally allowing some suboptimal actions to learn that unknown environment and find the optimal action at the end of the day. Here, what we're going to cover in this course is, I would say, mainly supervised learning, but the tools that we're going to cover somehow can address all of them, because essentially we are talking about optimization in a general setup. And then whenever that you have these form of optimization problems, definitely you do have in all these settings. So whenever you do have that, then you can say that, okay, this is the application of this course in that learning setup. So just imagine a reinforcement learning over a network which is modeled by Markov decision process of many states space, very big state space, and then you want to optimize over that. So you have a lot of decision variables there that you want to optimize over. So there you have a problem of large scale optimizations, the things that we're going to cover here in this course. Okay. Any questions so far? No? Okay. The easiest mapping of what we say in the generic setting of optimization and those three divisions in the machine learning is the supervised learning class of problems. So generally speaking, in this class of problems, we have an unknown target concept, which is, let's say, H, a mapping from X to Y. And this class is coming from this specific function or concept comes from some class of functions. And that class could be, I don't know, some labels, discrete labels, 0, 1. Something exists or something doesn't exist. Or it could be some real number for the regression. What is the value of this building, for instance? Price of this building or whatever. Okay? So H comes from some space of calligraphic H, and we are given a training examples, a data set of training examples, vector X, so boldface small font is vector here, and some Y, real values Y. And then we are given a hypothesis space, a space of the functions over which we're going to find some good representation of the actual mapping, okay? And then we are given a learning algorithm. And then the whole idea of this supervised learning together with some solution algorithm is to find a final hypothesis which would be as close as possible to this H. So this F is the function that our algorithm will output. It should be as close as H, and then this closeness will be measured by some either statistical or deterministic distance measure. You may notice here that the hypothesis space comes from F, not necessarily H. It will be clear in the next slide anyway, but it could be due to easier mapping, for instance. Just imagine that H is the space of all continuous functions, and it could be very hard to optimize over that. So what you can do is that instead of that, you can optimize over a space of linear regression, so the space of just linear functions, with the hope that you can find some function in the linear function space which would be very close to that function in the continuous space. Okay, the thing is that you don't need to be close to any function. You just need to be close to H, which is the unknown target. Okay, and then you have some samples of H through this data set. Okay. So this is actually a bit more formulation of whatever is said. So again, you have a training training data set of n samples, and you're going to have some form of predictions f of x, and then just assume that this is, let me use this one, I guess that this is, okay. So this is the loss on a single observation, and then some examples of the loss function. So let me write it down. This specific loss function, just, I don't know, assume quadratic loss, for instance. Then in the quadratic loss, let's say L of I is equal to, I don't know, y of I, which is the true value, minus f of x of I, which is y hat of I to power 2, OK? But it doesn't have to be in general. Let's say let's put norm here. It could be quadratic loss, or it could be norm 2 and then norm 1. But actually, this is the square of norm 2. And norm 1, yi minus f of xi. So these are two very simple losses. But what are the main difference between them is that let's consider this specific example. So this is like this, yi minus f of xi. This is something like that, and then this guy is something like that, right? This is something like that. So this is a linear loss, and then here you have very small loss here, but then quadratic loss here. Well, everywhere is quadratic, but then here you have an overwhelming loss if you move apart from some points like this, okay? And it's really important usually in machine learning or in general optimization to choose the right loss function. Why? Just consider this specific example of, I don't know, let's say you have these two classes. So just assume that you have two classes. Let's put here, OK? And then you have two very big outliers, here and here, OK? And then the whole idea of training is to minimize the loss function over that. So find, let's say, the best linear regression. In the linear regression, we will say f of x is w transpose x. Okay? Find the best w that minimizes the total loss that we can get here. So the total loss is parameterized by w is 1 over n over, well, this is essentially set, okay, of yi minus w transpose xi to power 2. Okay, so you're going to minimize this guy if loss function is this guy, and then you can just replace that with that if you want to have norm 1 loss function. So, but then what would be the difference between these two? So if you go with something like that, then the decision criteria, so if you go with norm 2, due to these two guys, it's going to look something like that. So that's going to be the optimal, let's say. You're going to see that anyway in some home computer assignment, but then the optimal solution going to be something like that. Why? Because it will allow some misclassification here. Misclassification means some loss, right? So essentially, and then the decision boundary is this guy, and decision criteria is if x w transpose x is larger than 0 or larger than 0, go, I don't know, blue class, and w transpose x is smaller than 0, then green class. So this is the decision criteria. And then the loss that you can have, for instance, here, let's say this is a loss here. And then the loss that you can have is the square norm of this guy. But then, since the square norm here is very small, so let's say this is actually yi minus w transpose x, right? Since this is very small, then you're going to regret a bit. But then, for this guy, what happens is that here you have this value here, let's say d of I. Let's call it d of I. Here, you're going to regret a lot, right? Because this is the exponential part. Well, very, very high value of this quadratic loss. Then what's going to happen is that due to just these two outliers, then these two just shift the whole decision boundary toward this guy, because you're going to somehow try to reduce the loss that you will see here. But then what would happen if you change the loss function to this is that you are much less sensitive, because the penalty that you are paying for this is just a linear penalty. So then in that case, decision boundary would be most likely something like that, a much, much better decision boundary. So this is just on the importance of loss functions, okay? But in general, you're going to have some loss functions. So this is something that you need to decide. Okay. And then let's first go with this. You're having a training error, which would be the average of the error. Well, you can have many different definitions, but then this is let's say the de facto definition of the training error, or which is somehow empirical risk. So the loss that you will see on an individual example on the training set, and then the average of the loss that you're going to have. Okay. But then what you really need to optimize over is, or let's say design your function based on that, is that guy, test error. So this is the loss that you're going to have on some sample x, and then the expectation of the loss over the joint distribution of x and y. But then why you're not optimizing this and you're optimizing that? Any idea? Because this is what we do at the end of the day. So we are optimizing over that instead of optimizing over that. But why? Yes. So the thing is that we don't have the distribution of the data. So we don't have any way to find that expectation, right? The only thing that we're given by the setup of the problem is just a data set of input and output. So we minimize this guy as an approximation of this guy and hope that it works. But does it? Well, we don't know. But then we hope that it works. But then there are some theoretical justification. The main reason actually is that under some simplifying assumptions, then this guy L hat is a Monte Carlo approximation of this L, and then you can bound the deviation of these two guys. So for instance, if we assume that same joint distribution will generate these samples on the test, that's something that you will not see in future, that comes in future, and then you want to operate on that. If the distribution that generates x and y in future is the same as the distribution of the training samples, this D, if they are the same, first assumption. Second assumption, if the samples are IID, the samples in the training examples, if they are IID, then you can say that this L hat is a Monte Carlo approximation of L. And then you can use some form of concentration inequalities, like Hofstadter inequality, to bound the deviation of these two. But just as a footnote, you really don't need those assumptions. So even if the distributions are different, you can use something called transportation inequality to bound the error. So if you minimize this guy, then you can bound the error on some L that generates by some other distribution. So you can use that. And then you don't need that IID assumptions. You can relax that a little bit. But this is the whole idea. So the whole idea is that we're going to minimize this guy with the hope that whatever we find, so what is the output here? By minimizing the output is just f. So the f can work very well with this objective function. So this is the whole idea. Just to make everything much easier from now on in the course, assume that w is a vector that parameterizes both h and f. So from now on, we don't have h or f. We only have this w. And then we want to optimize over w. So finding f really means finding w there, OK? And then let's say W star is the solution of our algorithm. At this point, we don't have any algorithm. So this is a generic algorithm. And let's say W star is the solution of that. OK? Then f of W star is the function that you will find. OK? So this is the output of the algorithm. Mean of f. So let's use this guy here. Mean of f, this is nothing, but let's call it h of w or whatever. Okay? So let's say that this is the true function that we want to find. And this deviation here, f of w star minus h, is actually the error that we saw here. So closer they are, well, actually, let's say, just to make it even more clear, let's put examples as well. So f of x parameterized by w star minus h of x, let's say in general. Okay. So for any sample x, then this is the output of your algorithm, and this is the output of the nature, so to say, okay? Or that target, unknown target function. And this is the difference. And then you want to minimize that guy, or make this one as close as possible to this guy, okay? We can always write this as just by adding plus and minus of this guy, then you can write it in this way. Just note that here, for instance, we're optimizing over the space of RD, whereas here we're optimizing over some other space. So as I mentioned, this could be a much bigger space than this, and this W, for instance, it can be the class of linear functions. Okay, why we're doing that? Because from the optimization perspective, it can be much easier to do that. It's much easier to optimize over linear functionals than a general continuous space. So if we do that, then we can somehow interpret these two terms. So let's start first from the second term, which is the minimum of f of w. So this is the true minimum of the function in that class of functions. We may not be able to reach that due to very bad algorithm implementation, okay? But this is the true minimum of the function within that class, and this is again h of x, okay? So this is like the approximation error, we can call it. So this is the error that is only a function of the expressiveness of our class of functions. So if our class of functions is not expressive enough, namely, if the class of function cannot, let's say, let's consider, for instance, okay, I'm going to need this one. Let's say these are the samples, okay, and I want to find this. So these are, let's say, h of x is x squared, and then I want to find f of x w transpose x, okay, for some constant w. So class of linear function. Then there is no way that I can approximate this guy very well. So it just doesn't matter if the line is here, the line is there, or line is there. Then there's going to be some error. And it just doesn't matter what is the optimal line here. So why is that? Because this class of function, at least the way that I wrote it, okay, this is not expressive enough. So then we're going to have, it just doesn't matter what is the optimal solution of our algorithm, there's going to be some bound on the approximation error in this case. But then if we just change this class of functions, then we may be able to reduce this guy to 0. And then it's really easy to say that this cannot go smaller than 0. Okay. It doesn't mean that if the approximation error goes to 0, doesn't mean that we are ending up to a good solution at the end of the day. It just means that the approximation error is 0, but then we may not be able to find this guy algorithmically. So the good thing with neural network, for instance, is that there are lots of works to say that neural networks are universal approximators. What does it mean? It means that if this W is the class of neural network functions, the space of neural network transfer functions, and this F is one of those, one generic formulation for that class, then this can approximate, can be as close, so this guy minus this guy can grow to 0, arbitrary. So this is, so then the approximation error can go to 0. Still, it doesn't mean that we would be happy with the solution. It just means that theoretically, we could be happy with the solution if we would have a very good algorithm, okay? In this course, we are not actually covering approximation error almost at all, okay? We are mostly considering estimation error. The whole idea is that this class of functions are expressive enough. So they are somehow designed very good to be a good class of functions, okay? But then, what is estimation error? The estimation error is the output of our algorithm, whatever the algorithm is. But then the output of our algorithm minus the best functions that we could find in that class of algorithms. For a neural network case, we know that the best function could be any function in a space of continuous functions. So it could be anything. But then we might not be able to find that. And then there could be lots of reasons for that. For instance, if I say that this is my function, okay, and I want to approximate this guy by a neural network or any other functions that is expressive enough, okay? But then I'm just giving you just one sample. Then there is no way that you can approximate this. You can say that the output is y equal to x to power 2, because you can have any other functions as well, right? So it could be due to lack of data sets, lack of enough samples in the data set. It could be due to poor quality of data set. It could be due to limited computational power or very, very, very challenging optimization landscape where you cannot find the optimal solution even if you do have enough computational power. So due to all those reasons, we may not be able to close this gap. So what we're going to cover in this course is actually targeting this gap to say under which condition we can close this gap. If we are able to close this gap, then what is the computational complexity? What is the memory requirement? What is the requirement on the data set, for instance, that you need to have? And is it even possible to do that if the optimization landscape gets a bit harder? So if we are talking about non-convex optimization, then moving that guy to 0, it's going to be very, very hard. OK. Yep.
With respect to moving the estimation error to 0, wouldn't that end up in kind of an overtrained solution and resulting in, let's say, we are going to try to make it to 0. That means that's defined for the set of data that you're trying to train and trying to find out. And if we get some additional values from outside, then we would end up not falling within that group. So
that's a good question. Actually, that's why we did need this guy. OK. So if I repeat the question, then essentially it says that is it possible to over-parameterize the function class? So let's say that instead of saying that going with the minimum W possible, let's go for an over-parameterized class of functions. So you have a lot of parameter to optimize over. And in that case, isn't it possible to go with estimation error 0 and approximation error 0? Yep, it's surely possible. But then the whole idea here, this is somehow at odds with these assumptions, right? So with these assumptions, we should somehow say that this guy is somehow approximating this, OK? And then through some tricks in the optimization, we should make sure that this is not happening. So what's not happening? Having an over-parameterized function and then trying to overfit on the data. We shouldn't do that. And there are some very standard ways of doing that. And then one of them is like adding some form of regularizers or whatever. But that's a good question. And actually, I'm not sure if this form of regularizers are the final solution, but then they work pretty well in practice. So what is it? Well, here in this slide, you will see some classic examples of objective functions that you can have here. So the objective functions that you can have here, for instance. From now on, f of x, let's say, just remember that f of x here is not exactly identical to the f of x in the next slide. Here, f of x is actually just this part. So from now on, we will say f of x is the objective function that we're going to optimize, which is a data fitting part. And then we want to make sure that the data fitting part will fit the actual function. But then to make sure that we are not, well, to do something more, we are adding this form of regularizer, usually. The first one, if we add, so here the data fitting is done by linear class of functions, so W transpose xi. And in this form, we are going with norm 2 loss, which is called ridge regression. Linear because we have a linear regression here, and then ridge regression due to this guy. But there are some historical reasons for that. So this somehow promotes a bit more robust solution. Why robust? Just assume that there are some noise on x, for instance. OK? Then what is the deviation on f if the noise in x is a bit high? Then you can see that there are if we don't care about this w, so if we don't restrict w to be smaller and smaller, then the error here could be large, okay? But then what would happen if we make sure, with this term, if we make sure that w is small, then it can somehow damp the noise on x. So whatever the noise in x is, it would not reflect so much on f. So then you will be happy. So the solution that you will end up would be a bit more robust to the noise in the input. So this is the whole idea of having this ridge regression. Not the whole idea, but one thing that it can do. The second option is lossy regression. We are not limited to this class. These are just some examples of the objective function that you may see. The second one is a lossy regression. And the last term is known one. And it will promote sparse solutions. And so for instance, just if I want to give you an example of what the solution would be. Just consider, I guess that space should be fine for me. Just consider a data of something like 0, 1 data. Doesn't have to be actually 0, 1, but then it should be just a sparse. So a sparse data, and then we want to minimize. We want to find a function in the linear class of functions, for instance, or even SVM or other classifier with the first objective function. Then the solution you're going to end up would look like something like this. So that is the solution that you're going to look like, that's going to look like. But then the solution that you're going to recover, well, here is, let's say, is the solution of ax equal to b with some sparse x. Then that's a solution that you would have with the first objective. The solution that you would have with the second objective is actually something like this. Well, under some conditions, of course. But then you can pretty well recover the original one. But then here you need to have a sparsity, which we don't have in many data sets. OK? The last example here is support vector machine for binary classification, which looks like that. There are lots of other variations where instead of this guy, you have 1 minus y iw transpose x, for instance. And then this is just one example with ridge regression here. But then you can have many other things. You can have neural network objective function here as well. It would not depend on the less number of parameters, but then you promote with less number of parameters. So you promote finding the solution that is sparse with that. OK? But then here, you don't promote that. By this guy, you promote the solutions that have a smaller norm. OK? And this solution that I have shown, well, here it's going to be much smaller. Actually, it can look like actually something like that, very small value here. But then the norm of this guy usually is smaller than the norm of this guy, because this is the objective function, and you want to minimize the objective function. OK, so that was about machine learning. You're going to see a lot of that later in the slides. But the most part of the slides and all the lectures are actually about optimization, I should say. Here is just a very, very rough overview of what we will see in the following 2 or 3 slides, 3 lectures. So, well, I have changed a little bit the notations of the slides. So if you can just download the newest version of the slides. So let's say the convex set. So some very basic definitions. We're going to go over all definitions later on anyway. OK, so here you have everything. Convex set, I don't know, something like that. Why this is not working? So something like that is a convex. Well, it's not convex due to this guy, but let's make it convex. So this is a convex. Essentially says that for any 2 points in that set, the line segment, any point in the line segment here, so this is x1, this is x2, and you can define some theta between 0 and 1, and the line segment, this point, which is x1 plus, well, theta x1 plus 1 minus theta x2, this point should belong to the same set of functions. OK? So one example of non-convex set is like this. set, which is non-convex because clearly you can pick these 2 points and then there exists some theta here, then the line segment would be here, so it's not convex. But then there is a notion of convex hull, which is the set of, well, if you pick the line segments of every point in that set, and if you find the union of all those lines, then you're going to end up the convex hull. So the convex hull of this guy is the convex set of all the points here. So this is the convex hull, and by definition of the convex hull, you're convex here. Okay. Why convexity is really good here? Because you can have some very strong conclusions in convex sets. So you can have, we will see later on, but you can say that if something, you can actually show that if something is locally optimal, and if that optimization surface is convex, then it's globally optimal. So if you find a local minimizer, then it's global minimizer of that function. And this is a pretty strong conclusion. Okay, convex function is, well, the same thing in general. You can just, well, with duality, you can map them. But then this is a function. Can you see that? Okay, let me use blue. So this is a convex function. Essentially, if you pick any 2 points, x and y, the line segment here should be an upper bound of the function, all the points in the function here. Okay? So here, for instance, theta of x plus 1 minus theta of y, which would be some point here. For different theta, it's going to move here. And then the function at this point is f of theta of x plus 1 minus theta of y. So the function should be smaller than that. And this is the meaning of this. And concave is minus convex. So if you have a convex function, then you have minus of that is concave. The notion of epigraph. So for this function here, epigraph is this set. So this is epigraph of this f. And then you can just show that if function is convex, then the epigraph of that is a convex set. Okay? We need epigraphs for some proofs in the duality. We need that. And then you can go with the notion of a strictly convex function where this inequality here holds with just a smaller. So a strict inequality, then we have a strict convex functions. So that is the first, not homework, but optional homework to prove these two. Well, these are very, very, very good, especially this one, actually. They are pretty general form of Jensen inequality and pretty important for proving many theorems in convex optimization. And actually, the main things that you're going to use is a bit more advanced version of these guys. So you're going to need these as some elements to prove some other inequalities, and then use those inequalities to prove most of the convergence results in convex optimization, both deterministic and stochastic settings. Okay, but here, this is a bit more general version of this guy, because here you can just go with random. Just imagine that this is true, which is true, by the way. But then you can just go with this random value x, which takes theta. Let me see. Okay, here we have lambda, with probability, which takes x with probability lambda and takes y with probability 1 minus lambda. Okay? Then if that's true, then this is automatically true. So, and then how we can prove these two? So, well, this is very easy by induction. You can show that. And what about this? Have you seen the proof of this? I guess so. But you can use measure theory to prove that, but then there are some easier ways to prove that. Any question? So if not, I guess we can close right now and then come back in like 15 minutes perhaps, or 10 minutes. Okay.